Okay, welcome back again. Our next talk will be about GRHayL. I think you pronounce it in this way.
Yeah, that's
And
right.
it will be delivered by Leo Werneck. Leo is a postdoctoral researcher at the University of Idaho. He writes and develops high-performance software to solve complex PDEs. I took it from your website. So you have 45 minutes, and I'll let you know when you have 5 minutes left before the questions, and you can start whenever you are ready.
Okay. Thank you very much for inviting me. It's a pleasure to be here. I think it's my first time giving a talk at the European version of the Einstein Toolkit meeting. So before I start, I just wanted to say two things. So I'm really not a morning person, so I'm running on a lot of caffeine right now. So the pacing of the presentation might oscillate violently, and I apologize for that. The second one is that my not so camera shy cat might interrupt us at any point, and I apologize for that in advance because she really knows how to come at the most inconvenient times. But with that out of the way, I'm going to be talking to you guys about GRHayL. GRHayL is a general relativistic hydrodynamics library that we developed at the University of Idaho. It was primarily led by Samuel Cupp and I, and it has contributions from several PhD students, Terence Pierre Jacques, Johnny Tsao, and David Boyer. Um, and we are part of the group that is led by Zach Etienne, with contributions by Samuel Tootle and others as well. Oops. Okay, so I'm going to do a very brief motivation as to why I study binary neutron stars. I'm sure we heard a lot about that today, so I don't need to go into too many details. Um, let me just, my my face is on the way, and I don't know how to. Well, anyway. Um, the observation of GW170817 and all of the electromagnetic counterparts that we're seeing alongside it created a new frontier, opened a new frontier for multi-messenger astrophysics. Um, and current and future observations will probably increase our understanding of these phenomena and bring even richer data. But there are still several unanswered questions beyond what was already confirmed, right? That these events can lead to these electromagnetic counterparts. But the main ones are, for example, what is the equation of state of extreme nuclear matter? How does the dynamical ejecta from these systems produce kilonovae, or explain the our process element abundances? So a typical simulation of these systems will be consisted of three um, phases, where we sometimes distinguish them as three distinct phases. The first one is the in spiral, where there's um, you're capturing the last final few orbits of the merger, um, from separations that range from a few tens of kilometers. Um, and then that goes into a phase where the stars first touch, and a few things can happen. Either they can promptly collapse to a black hole, or they can create a hypermassive neutron star, which is this quasi-stable transient object that might oscillate for a little while before it collapses to a black hole. Or if the masses of the progenitors is not large enough to produce a star that is unstable, it might actually just result in a stable neutron star after some ejection of matter, perhaps. In this case here, I'm showcasing a scenario where a black hole was formed, and I've actually plotted the apparent horizon of the black hole there as well in the third plot. And then, of course, the payload of these simulations is always extracting gravitational waves and their electromagnetic counterparts. So the type of signals that we're looking for is what's depicted in the last picture. And there has been a lot of work that has been done over the past few years. I've made some contributions as well. And I'm sure there's a lot that I'm leaving out here, but there's a lot of physics that has to go into this, and a lot of codes have been developed to do these things. And it's important that in order for us to keep pace with this rapidly evolving field, that we have means to do reproducible work, and that can easily collaborate between different infrastructures and different codes. And that's partly why the inspiration for the development of GRHayL. Um, so again, from a numerical standpoint, right, and this is a massive oversimplification, but from a numerical standpoint, all that we need to do is solve Einstein's equations coupled to matter, right? So you're going to have a g mu nu on the left-hand side representing the space-time, and a t mu nu on the right-hand side representing the matter distribution. In this case, for neutron stars, is just represented by a magnetized fluid, relativistic fluid coupled to gravity. And so basically all you need to do, right, is communicate space-time to the GRMHD field so that you can do the evolution of the GRMHD fields. And once the GRMHD fields are evolved, you communicate back and just so on and so forth. Just a very crude way of viewing how these things are done in the computer, right? So the starting point for this talk is IllinoisGRMHD, which is the predecessor to GRHayL, right? So IllinoisGRMHD is a rewrite of the original GRMHD code developed by the Illinois Numerical Relativity group. It's leaner and faster than the original, but it agrees with it to round off error. So the IllinoisGRMHD has just a few thousand lines of code as compared to tens of thousands of lines of code from the original code. It provides GRMHD for fully dynamical spacetimes in the form of an Einstein Toolkit thorn or module. It's open source, part of the Einstein Toolkit, and it has been field tested to model many different compact object systems. And that includes single and binary neutron stars, black hole accretion disks, black holes and neutron star binaries, and white dwarf binaries involving white dwarfs as well. So this seems like a very good starting point. Of course, there is the complication that IllinoisGRMHD, as the Einstein Toolkit module, has idiosyncrasies that were put into it because it was developed as an Einstein Toolkit module, right? And so, particularly if you are a new student to the code, you might feel like the code is too smart for its own good. So it knows how the Einstein Toolkit wants to do things, and so it does things in places that it shouldn't, and it relies on some behaviors of the Einstein Toolkit at times. And so for a new student, it's very hard to know at first glance where the Einstein Toolkit ends and the module begins, and things are very intertwined, I would say. So this is one of the primary motivations of GRHayL, right? We have a monolithic code base in the form of IllinoisGRMHD, I would say. The Einstein Toolkit is great. It's providing the infrastructure with all of the things that we need. But because of the way that things work, it's much harder to debug. If you have a simple thing in one of your helper functions inside the GRMHD thorn, it can be a pain to debug what exactly is going on given the complexity of the infrastructure. And the way that IllinoisGRMHD is developed or was developed, it makes it hard to make it future proof. Depending on what you want to add, and you might introduce changes to the code that are undesirable, and the APIs were never made to be, consolidated and user friendly. It was just whatever worked. And so with that comes a steep learning curve, right? It discourages community adoption, even though for people that are interested in just using the Einstein Toolkit, all you need to do is download an example par file, slightly perturb it, and there you go, you're ready to use it. But most people that use the Einstein Toolkit tend to actually do modifications to these modules in order to achieve slightly different behavior to study different systems. And doing that with a code that was not meant to be modified, it can be very difficult and requires a lot of knowledge from things that are not the primary focus, which is the physics. And so we always try to create this analogy that the way that the original IllinoisGRMHD looks like is like this tangled octopus, where it's really hard to distinguish between, again, the infrastructure and the actual code at times, right? Not at all times, but at times. And what we try to do is remove that, right? So GRHayL, not GRHayL. I've heard that a few times. So GRHayL is the general relativistic hydrodynamics library. It refactors IllinoisGRMHD into modular components. So GRHayL is the future of IllinoisGRMHD. In fact, the latest IllinoisGRMHD inside the toolkit is already based on, it already uses GRHayL. And it has, a lot of niceness associated with it. So better documentation. It's much easier to learn. It's much easier to contribute and extend. And it is infrastructure agnostic. So you can think of GRHayL as sort of like a numerical recipes for GRMHD, right? And it's provided in the same akin to things like a GSL, right? Where you just compile a library and link against it, and now you have all of these GRMHD functionalities that might be interesting to you. Um, and when developing GRayL, we try to adopt, four concepts that guided us through the development, and we try to enforce that very strongly, which is that we want to make it easy for new users to use the code and to extend it as needed. We want the code to be as modular as possible, and extensively documented. And we want it to be infrastructure agnostic, right? So these are the four pillars that define the guiding principles that helped us develop GRayL. And we find that some of these are easier to do than others. Um, but we believe we achieved relatively good success in all of these. And we have some good examples, particularly of the first one, which is our biggest goal, which is to make it easier for new users to use the code and extend it as needed. Um, so it is a known fact for people in numerical relativity, right, that new students are burdened with a lot. And so they have to go through the process of learning a lot about physics. It's not just numerical relativity. You have to know astrophysics, you have to know numerical methods. There's a lot, right? And on top of that, there's a lot of math involved too, and there's a lot of computer science, right? I don't think a lot of my colleagues have thought that they would be worrying about CPU caches and race conditions when they're talking about, oh, I'm going to be solving this interesting astrophysics problem in the computer. But here we are, right? And we kind of recognize that the weakest link for newcomers in the field tends to be the computer science aspect. Even if you're very good physics students, you might not have a lot of experience with dealing with complex applications like the Einstein Toolkit and things like that. And so our proposed solution, again, is guided by the fact that we want small modular code pieces. We want to focus on the code and not the programming language. This is something that, there are some new programming languages out there that are trying to do the same. Sometimes I think we spend more time debugging our knowledge of programming languages than the actual application, which is, not great, and extensive documentation. So this is how we're trying to address this uh, as much as we can. So the way that we achieve this or address each of the problems, right, is again the small modular pieces are provided in GRayL as self-contained modules, which we call gems, like a gem encrusted GRayL, right? And you can think of something like that. We try to use no obscure language features, and by that, we chose the simplest language. Arguably, it's not. I mean, we use C, so it's simple in the sense that it's a small language. There's not a lot. It's not a full-fledged language. Its library is not highly extensive, but it's very powerful language. It still takes a long time to learn, but you usually spend more time understanding the application than to try to understand a difficult templating or what's the compiler doing with this particular case. And we provide good extensive documentation in the form of wiki pages for all our gems and for all our functions. And recently there has been some progress to actually create Doxygen documentation as well. It's not fully done, but we're working on this. This is active development. So the goal, right, is to get this tangled octopus and turn into this nice cuttlefish that has been completely detangled and makes it clear what where things begin and where things end. And so to that extent, this is a slide that I showed before a few times, so apologies if you have seen it already. But the idea is that you start with your core code infrastructure. So it can be, Cactus or the Einstein Toolkit, or it can be in BlackHoles at Home in NRPy, or your own infrastructure. It can be really anything. And then you have, some of the gems that are inside GRAIL. So for example, you're going to have a gem that only deals with conservative to primitive routines, one that only deals with reconstruction, right? As we evolved GRMHD fields using a flux conservative scheme. And so that required, and typically all of the GRMHD quantities are self-centered, where normally on the grids, and whereas normally the space-time quantities are vertex centered, and so you always need to do reconstruction on different faces of the grid. And so we have a gem dedicated for that. Then we have another gem that is dedicated to computing GRMHD or HD fluxes and sources. One just for the induction equation, that's if you're going to include magnetic fields. One for the equation of state. One for neutrino physics. And then we have other physics that can be added as well. Um, and with the exception of the equation of state um, gem, everything else is completely independent. So everything depends on the equation of state gem, but it's also relevant to say that you don't have to use the equation of state gem that we provide, so long as you create a few wrapper functions that provide functions with the same signature as GRAIL expects, you can actually plug in any EOS infrastructure and GRAIL would just work. We do that by having some function pointers that allow you to change things at runtime. So the way that you communicate data between the core code and the gems is through C structs. There we have some helper functions to help you pack and unpack the data, and it's really we try to make the API as intuitive as we could. If you find that that's not the case, please let us know. We'd be happy to revise some of them. But the idea, right, is that this creates this interconnectivity between the code and the infrastructure. Now, it's important to say as well that with GRAIL, it's not as a proper library, it's not something that you need to actually use all of it. So if for some reason all you wanted to use from GRAIL in your infrastructure is the equation of state gem, you're allowed to do that. If all you wanted to use is the neutrino physics, as long as you provide some of the EOS connectivity that we need, then again, you can just use the neutrino gem. So you can pick and choose which gems you're going to use inside your infrastructure, keeping in mind that the equation, that everything kind of depends on the equation of state, or almost everything. That's the only subtlety. So of course, it, it would be in a tragedy to not go over how we actually validate GRAIL, which is one of the points that actually takes a long time to do. So basically, the way that we have done this is to consider IllinoisGRMHD our trusted code. And so we start our validation process by generating some random input data and then running it through functions inside IllinoisGRMHD in GRAIL, right? So we run that random initial data through GRAIL. Then we run it through IllinoisGRMHD. And again, it doesn't really matter if the data is physical, right? At this point, for some of the tests, it's important that the data is, because otherwise the results might not be very sensible for us to analyze. But for most of them, we just care that the functions have the same numerical behavior. So long as we can ensure that the functions are producing the same output, we have validated that we are at least reproducing what IllinoisGRMHD was doing. And then once we have these two outputs, we actually get the initial data and perturb it at round-off level, pass it through IllinoisGRMHD again, and that basically creates a two results from IllinoisGRMHD, which is a IllinoisGRMHD trusted and a perturbed. And these two outputs create a bound for how much from the trusted result is the GRAIL output allowed to deviate. And so basically that's where we compare. So instead of just saying that the GRAIL output should agree exactly with what's coming out of IllinoisGRMHD, we say that it should fall within a range that is IllinoisGRMHD and IllinoisGRMHD perturbed, right? Hopefully that makes sense. Um, we also have integrated continuous integration into our code base with GitHub Actions. And we try to make sure that we handle multiple operating systems and compiler combinations. And we use the trusted output, like I mentioned, to validate the test outputs with every commit. And every PR goes through this as well. So the core functions have individual unit tests. And the beauty of having it as modular as we can is that we can do tests at very basic level. So for example, if you have, a tabulated equation of state module, a big part of that module is going to be reading in the table and performing interpolations in three-dimensional space, right? So you have a table that is typically tabulated in baryonic density, electron fraction, and temperature, and you're going to be doing three-dimensional interpolation on that table in order to obtain pressure and specific energy density and things like that. So a core algorithm that needs to be validated is whether your interpolation is working correctly, right? And that can be done independently of the equation of state because this is just a 3D interpolation algorithm. And so we have unit tests for that. Um, and so and we have these little badges in GRAIL that tell us how well we're doing. And so far, our code tests indicate that we have 93% coverage of the code base. Some of these tests, like I mentioned, are some of the reason why we don't have 100% is because a lot of the functions are designed to check whether or not we have hit a bad condition. So there are a lot of if statements that are difficult to trigger. And so we sometimes have to write tests specifically to trigger error conditions inside of functions, and that can be time consuming. But we're working on, pushing it as high as we can. So GRAIL has several implementations already. So we distinguish between GRAIL, the library, and GRAIL implementations as codes that use GRAIL in them, right? So the library itself is mostly oblivious to the grid structure, meaning that the library doesn't really care if you're doing your work in Cartesian coordinates, in spherical coordinates, if you're parallelizing with MPI or OpenMP or Charm++ or whatever, right? Uh, and that's because most of the codes, if you think about your own infrastructure or infrastructures that you're familiar with, when you think about, for example, primitive recovery, it's a pointwise operation for the most part of it, right? Unless you're doing some higher order method. If you're thinking about just second order GRMHD, which is the most common out there, then recovering primitives is just looking at one specific point in the grid and analyzing the conservative grid functions and recovering the primitives, right? So the function that is actually doing that is not, it doesn't care about the rest of the grid. Um, so yeah, it doesn't care, like I said, about whether or not you have done parallelization across multi nodes, how you have done your patches or whatever, right? Or the coordinate system either. And because of that, we can actually make our functions are all very GPU friendly, right? Because these little kernels can be very quickly changed to actually make it work with CUDA or other or HIP, for example. And in fact, we have a lot of progress done towards that. We're at the final stages of making it fully GPU compatible at this point. Now, if you have worked on GRMHD before, you know that this can't be true for every part of the GRMHD code because after all, if you're computing fluxes and sources, those involve derivatives, right? And so whenever, or if you're doing reconstruction, you're typically performing in some form of interpolation that, with some shock capturing scheme. and that typically requires you to look at multiple grid points. But GRayL can get away with simply requesting the user to pass it a little stencil, right, with points across a specific direction, X, Y, or Z, for example. Um, and again, it doesn't have to be X, Y, or Z. It can be R, theta, phi if you're in spherical coordinates. And GRayL doesn't really care about that. All that it cares is that you give it a stencil in a particular direction that you want to do reconstruction, and it's just going to do it for you. So even in the case where you actually need multiple grid points, it's still somewhat agnostic to the grid infrastructure. Um, and so what GRayL implementations need to provide, therefore, right, is basically the opposite of everything that I just said, right? So it needs to provide the loops, right? It needs to tell that's where you're gonna see oh, well, now I'm going to loop over the interior grid and I'm going to compute the fluxes and sources, right? That's not going to be in the library because the library doesn't care about that, right? How to access grid functions. So codes have different ways of accessing grid functions or different data structures to store the grid functions, right? And again, GRayL doesn't make any assumptions of that. So long as you can pack your data into a simple C struct, you can then use any of the GRayL functions or function scheduling, right? So GRayL doesn't tell you how to do, oh, now I'm going to do counterprim, and I need to do that before I do the fluxes and sources because I need the primitives in order to compute the fluxes and sources. Again, GRayL is not going to tell you how to do that. It's just going to provide you the functions to do that. Memory management, there are no, other than I guess for reading HDF5 tables. There are no mallocs and free in GRayL because we don't do any of the memory management. Um, Parallelization is also not part of GRayL, and I/O. So all of this are things that have to be provided by the infrastructure, and it's typically provided by the infrastructure, right? Nobody that is or most people writing Einstein Toolkit thorns don't have to worry about this either because Cactus just handles it all for you. Um, And so with GRayL, we gain, there are a lot of things to gain. In particular, if you compare GRayL with the original IllinoisGRMHD, so on the left you have IllinoisGRMHD, and on the right you have the GRayL-based IllinoisGRMHD. What you find is that the new version uses 40% fewer grid functions than the original. And this was done mostly by fixing inefficiencies in the original code that were unnecessary. So the original code had a bunch of auxiliary variables for computing BSSN quantities, and I think that's the main game. But it had some unnecessary temporary variables for variable reconstruction as well. And so we got rid of many of them, and that provided a big reduction in the memory footprint of the GRMHD code. It can provide up to 30% speed up in simulations in the Einstein Toolkit. Most of this comes when doing tabulated equation of state simulations. But even for hybrid equations of state, which are analytical equation of states, we see 10 to 15% speed up in the simulations as well. And this comes from mostly removing convoluted logic that we're doing unnecessary work. Some of the low-level kernels have also been optimized a little bit by removing some technical debt that was still present in there. There was some unnecessary conversions between different um, conventions for the magnetic field. So some conventions for the magnetic fields will divide by factors of 4 pi and others will not. And so within our code, we would translate things between, IllinoisGRMHD into a format that was compatible for Harm 3D, but then into a format that was compatible for the Harm 3D primitive recovery. And so that required three conversions, which often required dividing and then multiplying again by 4 pi. But because things were so convoluted, it was difficult to even notice that that was happening. And that's now all gone. And the biggest thing, which is the thing that we're proud of, is this 90% reduction of new GRMHD code implementation time. And I'll back that by saying that so Terence Pierre Jacques, it was a PhD student at the group that just recently defended and gotten his PhD. Here comes my cat, as promised. Um, So he developed a code called Groovy, which is which provides so it's a code that performs GRMHD simulation or GRHD simulations in arbitrary curvilinear coordinates in black holes at home, which is the infrastructure generated by NRPy. And he developed that code from start to finish, fully tested and running, full 3D simulations in I think just under 3 months. I think it was actually around 2 months. And if you compare that with a typical development cycle of a full GRMHD code from scratch, that can go between 1 to 2 years. There's a significant reduction in development time there. And so our main implementation, like I said, is IllinoisGRMHD, right? And I just wanted to give you just a quick look at a code. It's not going to be fully apples to apples. I apologize for that, but it's just this was the closest one that I could find so that you guys can see a little bit of GRayL in action. So this is a part of IllinoisGRMHD where we're doing conservative to primitive reduction, right? There are a few blocks here. So the first block is just the basic includes required by the infrastructure, right? If you ever programmed in the Einstein Toolkit before, you have to include this cctk.h files. And then you include this GRayLib.h. And GRayLib.h is the Einstein Toolkit thorn that we have written to allow users to interact with GRayL. And then you have this function called IllinoisGRMHD hybrid entropy conservative to primitive, which is a scheduled function. Inside that function, you're going to see a loop. This loop is looping over the interior of the grid. You have this index, which is how you're going to access your grid function indexes. And then you have a declaration of the conservative quantities initialized to 0. And then you're setting, the density, the conserved density, the conserved energy, the conserved momentum, and the conserved entropy. And then you're calling the counterprim multi-method. So in GRayL provides, you don't have to do it this way. You can call the manual routines if you want. But GRayL provides this counterprim multi-method, which is a wrapper function that will call a list of counterprim methods in order as the previous one fails, right? And that's a user-specified list of counterprim methods. So it will, for example, call, Noble2D, and then if Noble2D fails, it will call Noble1D, and then if Noble1D fails, it will call a routine called Palenzuela1D by the Palenzuela et al. Group, and so on, right? And so this is what the code kind of looks like in the Einstein Toolkit, right? And you're going to have a primitive struct that is going to have results coming out of it, and then you're going to have to unpack it later. And now I'm going to show you in the next slide what does this code look like in BlackHoles at Home, which is a completely different infrastructure, right? So BlackHoles at Home is, at least for the version that I'm going to show you now for Groovy, it's a unigrid code. It doesn't have AMR in it. It's still heavily inspired by the Einstein Toolkit, so there's going to be a lot of similarities. But hopefully you see that the difference between this and that is very small, right? So if I just keep flipping back and forth a little bit, right? You see that obviously the includes change. We don't have the GRayLib.h file when we're dealing with the library explicitly, so we have to do a little bit more includes. The intrinsics functions is something that is coming directly from BlackHoles at Home. But then you see here that you have a conservative to prim in spherical coordinates now, right? So it's not anymore Cartesian coordinates as it was in the Einstein Toolkit. And yet the loops look pretty much identical, right? Of course, the infrastructures have different names for what end go zones look like, but they still look the same. The way that we access the grid function index is also slightly different. But then beyond that point, right, you're just going to call the same initialization for the conservatives. Of course, you're changing the grid functions there because they have different grid function names. And then you're gonna call a counterprim tabulated multi-method. So even though I'm using a completely different equation of state here, this is a tabulated equation of state, you can still see that the code is basically the same, right? So I moved from an infrastructure that did Cartesian coordinates and hybrid equation of state to one that is doing spherical coordinates and tabulated equation of state. And you can still have a pretty much one-to-one comparison between the two, and it's relatively easy to follow. Um, so hopefully that motivates why we worked so hard on developing something like GRAIL. Um, and so the current implementations that we have for GRAIL, meaning the current codes that use GRAIL in them, right, are IllinoisGRMHD, and we have versions for both Carpet and CarpetX. We have GRAIL HD, again for Carpet, CarpetX, and NRPy. So GRAIL HD is a simplified version of IllinoisGRMHD. You can think of IllinoisGRMHD as GRAIL MHD, right? And so it's a simplified version where we completely get rid of anything that refers to magnetic fields. And so you get a leaner and more optimized code that is even simpler to read because you don't have to do the reconstruction associated with the magnetic fields.
Leo, you
We
have
have,
5 minutes left.
okay, thank you. We have NRPy leakage ET, which is a code that provides neutrino leakage. It actually works for NRPy as well. I don't think we have tested it with CarpetX though. Have Tavala, which is an initial data solver, and Tavala itself is also infrastructure agnostic, but we have an Einstein Toolkit module for it. And then we have Groovy, which is a GRHD code for BlackHoles at Home. And actually, GRAIL is also being used on Manga, which is implemented in the Chunga infrastructure and provides unstructured mesh GRHD, basically. And future infrastructures that might be interested in using this, we have talked to the authors before, are GRChombo, DenderJar, and perhaps your infrastructure, right? If you also want to do it. So I'm going to go very quickly through some results that are part of an upcoming paper that we're writing on this. It should come out relatively soon. So first one is just a series of the so-called Balsara tests, which is just, shock profiles and how they are handled numerically. So here on the left, you basically see a shock profile in the density and how different codes handle it. So GRHydro, which is the trusted code that we're taking here inside the Einstein Toolkit, and then a GRAIL-based GRMHD Thorn, both in Carpet and CarpetX, right? And on the left and on the right, you see that it captures the shock really well, and on the right, the errors are between the two different infrastructures, and meaning Carpet and CarpetX are of order 10 to the minus 7, so round off in single precision. Then just a series of results from the other Balsara tests, right, which have just different shock fronts in different places with magnetic fields now, where the first one is Balsara 0, which is Balsara 1 with no magnetic fields. Just going to go quickly through this. Then a series of TOV results. So on the left, we have results that actually compare two Einstein Toolkit Thorn. So IllinoisGRMHD, meaning the new GRAIL-based version, and IGM, which is the original IllinoisGRMHD. And we also have NRPy MHD, which is a Thorn inside which is a NRPy-based module that actually supports magnetic fields, but only supports Cartesian coordinates. And on the right, you basically have other TOV results that use. On the left, it's a simple polytropic equation of state, and on the right, the top is a piecewise polytropic version of the SOY equation of state, and on the bottom is the tabulated version of it. Then this is a plot that is a little bit, it's not that difficult to explain, I guess. But the idea is that the black curve is the result for the maximum density on the grid from a binary neutron star simulation performed with the original IllinoisGRMHD. Then we got the initial data and we perturbed it at round-off level, right? So this is the initial data that we're perturbing. And then we evolved it again. And the result for that maximum central density as a function of time is actually the orange curve. So you can see that there's a significant difference between the two. In particular, the black hole formation happens when there's a peak that is plateaued, right around 3,500 for the black curve and 4,000 for the orange curve. And then finally, the blue curve is the result of evolving this with a GRAIL-based IllinoisGRMHD. And so you can basically see that in terms of how the two compare, it's as if the new version is behaving as a round-off perturbation of the old code, right? And so just some results between the old and the new. We also see that the new code produces some improvement in the magnetic field. So if you look at the left panel of each of the figures, on the top one, you can see a lot more jaggedness at the top left, where the bottom one is a lot smoother. This is due to the changes that we've made into how we reconstruct the magnetic fields and to higher order derivatives for the metric derivatives. This is, again, it's sort of similar results, but for a piecewise polytrope equation of state, this is the moment where the stars first touched. And I can go back to this later if there are questions, but just a quick slide on the future of the code. So we plan to do more testing and support for CarpetX, which it already exists, but it's still a little bit limited. We want to go from GPU friendly to full GPU support, and that's well underway. Full tabulated equation of state support. Right now we support stellar collapse tables, but we want to do full compose tables as well. And we want to do built-in table cleaning based on the routines in Singularity EOS. And we want to add some more radiation transport to the code beyond what we have for just leakage. And resistive MHD is also something that we're interested in doing. So I think I might be going over time, so I'll just stop here.
Thank you very much, Leo, for the very nice talk.